Greetings! This video discusses the introduction to digital communications. First, we'll have a background of what communication system is. Next, we'll discuss the types of information. After that, we'll take a look at the different block diagrams for the communication systems. Next, we'll discuss the advantages and disadvantages of digital communications compared to analog communications. And finally, we'll discuss the different parameters concerning digital communications. A communication system, by definition, is a system model that describes the communication exchanges between two or more stations through a wired or wireless medium. There are two types of information that can travel through a communication systems. One is analog and the other is digital. An analog information, much like this analog signal, is a continuous signal for which a time-varying feature of the signal is a representation of some other time-varying quantity. Digital data, on the other hand, is a discrete, discontinuous representation of information. Therefore, at any given time, it can only take on one of a finite number of values. This is a basic block diagram of an analog communication system. On the input side, we have the source. The source can be anything that can produce an information. It can be a person, a musical instrument, a camera, or even a computer. The input signal here is the information that we want to transmit onto our destination. For example, if our source is a person, the input signal could be the voice of the person. If our source is a camera, the input signal could be the pictures of the camera. The input signal would then proceed to the transmitter. The transmitter processes the input signal to produce a transmitted signal that is suited to the characteristics of the transmission channel. The channel is the electrical medium that bridges the distance from source to destination. It may be a pair of wire, a coaxial cable, fiber optic cable, air, or even space. After the signal travels through the transmission channel, it will then arrive at the receiver. The receiver operates on the output signal from the channel in preparation for the delivery of the message to the destination. These include amplification and modulation. The noise refers to random and unpredictable electrical signal produced by natural processes, both internal and external to the system. Most of this noise gets into the system through the channel. Distortion is a waveform perturbation caused by imperfect response of the system to the desired signal. Interference is a contamination of extraneous signals from other sources such as power lines, machinery, and other transmitters. Now, let's take a look at the basic block diagram of a digital communication systems. Just like the block diagram of the analog communication systems, we still have the information source, the channel, and the information sink, which is our destination. The encoder transforms an analog or digital message into a new sequence of symbols that will represent the message. The decoder, on the other hand, converts an encoded message back into the original message. Now, you might ask, why should we develop a digital communication systems while we already have an analog communication systems? Well, here are a few advantages of the digital system. It is relatively immune to noise. It usually uses only two states of signal, therefore, it is simpler to measure and evaluate. It is easy to process and multiplex. It typically has higher information capacity, and it has higher data security. Now that we've seen the advantages, let's take a look at the disadvantages. It requires greater bandwidth. There is a need for ADC or analog to digital circuits on the transmitter side and a digital to analog circuit on the receiver side. This is in case the original information is analog to begin with. Next, precise timing or synchronization is strictly required. Digital communication systems. Digital modulation is the transmission of digitally modulated analog signals between two or more points in the communication system. Take note that the original signal may be analog or digital in nature, but the modulation technique employed is digital. This includes systems where relatively high-frequency analog carriers are modulated by relatively low-frequency digital information signals, and systems involving the transmission of digital pulses. Information theory. This is a highly theoretical study of the efficient use of bandwidth to propagate information through electronic communication systems. This is used to determine the information capacity of a data communication. There is a formula called the Shannon-Hartley theorem that we can use to calculate the information capacity that can pass through a given channel with a certain bandwidth. Information capacity. This is a measure of how much information can be propagated through a communication system. It is a function of bandwidth and transmission time. It represents the number of independent symbols that can be carried through a system in a given unit of time, often expressed as bit rate. The unit for this is usually bits per second, kilobits per second, megabits per second, and gigabits per second. You can see such measurements when looking at internet speeds, router speeds, or basically anywhere that involves the transfer of digital data. M-ary encoding. M represents a digit that corresponds to the number of conditions, levels, or combinations possible for a given number of binary variables. If a digit signal is given under 4 conditions, such as voltage levels, frequencies, phases, and amplitude, then M equals 4. The number of bits necessary to produce a given number of conditions is expressed mathematically as n equals log base 2m, wherein n is the number of bits necessary and m is the number of conditions, levels, or combinations possible with n number of bits. Baud. This is the rate of change of a signal on the transmission medium after encoding and modulation have occurred. This is a unit of transmission rate, modulation rate, or symbol rate. Baud is expressed as the reciprocal of the time of one output signaling element, and a signaling element may represent several information bits. Nyquist rate. Nyquist rate is used to describe the Nyquist sampling rate or the Nyquist frequency. This is the minimum rate at which the finite bandwidth signal needs to be sampled to retain all of the information. For a bandwidth of span b, the Nyquist frequency is just 2b. Frequencies greater than the Nyquist rate gets attenuated and appear at lower frequencies than they are really present in. This condition is known as aliasing. This is an example of a sine wave that is sampled only once every 3/4 of a cycle. The reconstructed sine wave appears to have a lower frequency than the original sine wave. This is known as aliasing. Let's have an example. Suppose we are interested in reproducing a waveform that has a maximum frequency of 6 kHz. What is the minimum sampling frequency to avoid aliasing? Let's recall the Nyquist rate. To avoid aliasing, our sampling frequency must be greater than or equal to twice the maximum frequency of our signal. In this case, the maximum frequency of our signal is 6 kHz. So the minimum sampling frequency is greater than or equal to 2 times 6 kHz, which is just equal to 12 kHz. So the minimum sampling frequency to avoid aliasing is 12 kHz. Power efficiency. This is the ability to preserve the fidelity of a digital message at lower power levels. In order to increase noise immunity, it is necessary to increase the signal power. The amount by which the signal power should be increased to maintain a certain bit error rate, or BER, depends on the modulation scheme. The power efficiency expresses the signal energy over the noise energy ratio required at the receiver to guarantee a certain BER. Bandwidth efficiency. This describes how efficiently the allocated bandwidth is used. Defined as the ratio of the throughput data rate per hertz, or BPS per hertz. The fundamental upper bound is defined with the Shannon-Hartley theorem, which is C over B equals log sub 2 quantity 1 plus S over N, wherein C is the channel capacity in bits per second, B is the bandwidth in hertz, and S over N is the signal-to-noise ratio, which is a unitless quantity. Let's look at an example. For a standard telephone circuit with a signal-to-noise ratio of 1000 and the bandwidth of 2.7 kHz, the Shannon limit of information capacity is... Now, let's take a look at this example. The value 1000 is not in decibel. It is already a ratio of the power. So we can directly plug this into our formula. This is our S over N. And the bandwidth is also given 2.7 kHz. So let's plug this in our formula. And then we have C equals 2700 times log sub 2 of quantity 1 plus 1000. And then we'll get the value of C equals 26.9 kilobits per second. Do not be confused with this kind of unit. It's kilobits per second, not kilobyte per second. It also applies to Mbps, it's megabits per second, and to Gbps, it's gigabits per second. That's it for the introduction.